Okay, so we are going to take a look at section 1.5 from the old textbook, which is relative motion or frames of reference and relative velocity. And relative velocity. Now we've taken a look at frames of reference and relative velocity in grade 11, and we took a look at them where we said how frames of reference depends on how we're looking at an object. It depends on the relative velocity depends on which perspective that we are looking at, and we're going to continue in that same frame in grade 12 as well. The only difference being that whenever we do questions now, when we're looking at relative motion and frames of reference, we will be doing vector components to solve these questions. Okay, so we will just review again one more time what frames of reference were and how we wrote them down. And the example is as follows. So last year, for example, if we were taking a look at an object, for example, like a boat or a plane in water or a plane in air, we would have drawn a figure like so. And we would have said this was velocity of the plane relative to the ground, velocity of the plane relative to the air, and velocity of the air relative to the ground. Something like this. And the way we write it down is we said VPG. So we wrote our first subscript, which stood for the plane. The second subscript stood for the frame of reference, which is the ground. So this is from Earth's perspective that we're looking at. If somebody was standing on the ground and they saw the plane traveling, how would they see it, and what would they see, their perspective? This was P2A, which was also known as the airspeed. The airspeed does not mean the speed of the air, rather it means the speed of the plane in the air. So this is the velocity of the plane, the object that is traveling, and this is the frame of reference, which is the velocity of the plane in the air. This is what the pilot, if they were in the plane, they would see their speedometer, their speed gauge telling them a certain speed, which is what the plane should be traveling at. And the last one would be the velocity of the air relative to the ground. This is also known as the wind speed. Okay, and this is when a wind is blowing in the air. For water, it would be the flow of the water, so which way the current of the water is going, and so on and so forth. This is how you would go about solving frames of reference questions. Now what we're going to do is we're going to take a look at one question or maybe two questions and go about solving them. And the one that I'm looking at right now is sample problem number 3, again from the old textbook. So let's erase this. So sample problem number 3, page 56, relative motion. And the question is as follows. The question says a helicopter flying where the average wind velocity is 38 kilometers per hour. So velocity of the air relative to the ground is 38 kilometers per hour. And you have this at 25 degrees north of east. Okay. It needs to achieve a velocity of 91 kilometers per hour relative to the ground. So this should be the ground speed of the plane, which is 91 kilometers per hour. And the direction here is 17 degrees west of north. And it says for the plane to arrive on time. What is the necessary velocity relative to the air? So we're looking for VPA. So the way we would write it down is as follows. We say VPG, which equals to VPA plus VAG. Now we have this, we do not have that. So what we're going to do, of course, is in algebraic fashion, VPG minus VAG, which equals to VPA. Now, of course, this is the vectors that we're looking at. So when we are subtracting vectors, what we do is we add the opposite vector, so plus negative VAG. So here's my negative VAG. This is how I'm going to go about solving it. So what I need to do is make sure that whatever vector I come up with, I flip it. Okay. All right. So let's draw these vectors out. So the first one is VAG, which is 25 degrees north of east. And this is going to be your VAG, 25 degrees north of east. Okay. And the next one, of course, is our velocity of the plane relative to the ground. Again, this is west of north. It's this way. And west of north. So this is VPG. And this, of course, is 17 degrees. Of course, this is not scale diagram, so bear with me. This is VPG dot X, and this is VPG Y, the vector components of it. Now, since this is our negative vector that we're looking at, what I'm going to do is I'm going to turn it around. So it should be going in the opposite direction. This is going to be negative VAG, and these are your Y negative and VAGX negative. Okay, so this is what we are going to start with. As I said, you can subtract the vector while you're doing the question as well. It's up to you. Okay, so let's erase this and let's continue with the question. And so we'll start with VPAX, which is made up of VPGX plus VAGX. Okay, and you end up with sine of 17 times 91, which is going west, plus cos of 25 times 38, which is also going west. Both diagrams, if you see, are going in the westerly direction. And you end up with 226.6 kilometers per hour going west, plus 34.4 kilometers per hour also going west, and you end up with a VPAX, which is 61.0 kilometers per hour going west. All right, we're going to do the same thing again for the other component, Y, VPGY plus VAGY, and you get cos of 17 times 91, which is going north, plus sine of 25 times 38, which is going south, and you get 87 kilometers per hour going north, plus 16.1 kilometers per hour going south. Of course, we're going to subtract the two vectors because they're in opposite direction. So you end up with a VPAY, which is 71 kilometers per hour going in the northerly direction, since the north vector is larger than the south vector. After this, what we're going to do is we're going to solve for it using Pythagorean theorem. Okay, so let us draw the components out. It's west and north, so it's going to look something like this. This is going to be your VPAX, and this is going to be your VPAY, and of course this is your VPA. So when we solve for it, VPA, which equals to the square root of VPAX squared plus VPAY squared. Solve for it, so VPA equals to, put the numbers in, and they are 61 squared plus 71 squared. And you get VPA, which is 93.6 kilometers per hour. Of course, we're going to do tan inverse to solve for our direction. Tan inverse, opposite over adjacent. And our opposite over adjacent will come out to 61 divided by 71. Okay, and you get theta, which is 41 degrees west of north. And this is your solution for relative motion. Now, as I said, the way to complete the relative motion question is very, very similar to how we've been doing our vector components questions all throughout this chapter. Now what I'm going to do is I'm going to take a look at one more question, which is sample problem number 2 on page 55 in the old textbook. So I will erase this. So this is sample problem number 2, page 55. Again, old text, Nelson Physics. And the question is as follows. It says the airspeed of a small airplane. So airspeed meaning VPA, which is 215 kilometers per hour. Okay, and the direction is not given, so we don't know what this is. Okay, then we're given the wind is blowing, which is the velocity of the air relative to the ground, at 57 kilometers per hour. And here it says it's blowing from the west. If it's blowing from the west, therefore it's traveling east. And determine the velocity of the plane relative to the ground if the pilot keeps the plane aimed in the direction of 34 degrees east of north. And here we're looking for VPG. So what is the velocity of the plane relative to the ground? And then to solve for this question, of course, what we're going to do is we're going to solve it in terms of our vectors. Draw it first. So you've got east of north, 34 degrees east of north, 34. This is my VPA, VPAX, VPAY. And of course your VAG is going in the easterly direction. This is your VAGX, only one. So what we're going to end up having is VPGX, which is made up of VPAX plus VAGX. And you have VPAX is sine of 34 times 215 plus this, nothing, we need to do anything here, so that's 57 kilometers per hour. That is going east. Of course, this is going east as well. So you can end up with a VPGX answer right here. Okay. Now we're going to do the exact same thing for VPGY, which is made up of VPAY plus VAGY. Now there is no Y component to my VAG, so this is 0. So you end up with cos of 34 times 215, which is going north, and you get a VPGY component. Now the remainder of the question is to be solved the same way how we solve all our vector component questions. So what will happen is, again, we'll draw this vector out, and you'll end up with something that is east and north. So north and east, and you'll end up with a VPG vector that is going this way. This is going to be your VPGY. This is going to be your VPGX. Then we'll solve for VPG, and VPG, of course, is going to be square root of VPGX squared plus VPGY squared. And you will end up with a VPG. The final answer, after you do all the work, comes out to 251 kilometers per hour. And your direction should be, again, tan inverse VPGX over VPGY, and you have theta, which is 45 degrees east of north or north of east. Either one of the two will work. So these are two questions that I just wanted to cover from chapter section 1.5 from Nelson Physics 12, the old version. Hopefully this helped. Thank you very much. Bye.